helps. Yeah, you can say that. Produce YouTube videos. All right, so today we started talking about Newton's laws. We're a little bit yesterday, and today we're going to do a lot more and do some examples. Newton's second law, I mean, these are really the laws of mechanics. If you really master these and all the applications of these, that's 95% of the class. The only thing that's not really part of that will be the last little bit on thermodynamics if we get there. So let's go ahead and I'll just write up what the laws are and we'll cut to the chase. So Newton's laws, there's only 3 laws, and all of mechanics are careful, logical deductions from these laws. All of the theoretical mechanics, and then it agrees well with experiment, and so that's what makes it a science. So one is the law of inertia, that in the absence of forces, on an object, the object will move at a constant velocity. Velocity. So that means same speed in the same direction. And that may be 0. You know, if it's at rest, it's a constant velocity too. There's a relation between force and acceleration, and that is that the total force on an object, F total force, is equal to the mass of the object times the acceleration of the object. The relation between 2 vectors.
The total force
Is equal to the, on an object, is equal to the mass of an object times its acceleration. And then the third law, this is going to be a little bit confusing, but suppose I have 2 masses, M1 and M2, and let's suppose that M2 somehow or other, it doesn't really matter how, exerts a force on mass 1, and I'll label that force F12. This is my label for the force on object 1 by object 2. Okay? Then the force on object 1 by object 2 will be equal to negative times the force on object 2 by object 1. So that means there'll be a same vector, same length, but in the opposite direction on that second mass, like that.
Is that what's like? Is that 2
This is on mass 2 by mass 1.
Oh, okay.
Okay? So this is a little bit confusing. We're going to go through some more examples of this, but this is really what the carefully writing what the third law means. And it gets stated quite regularly that every action has an equal and opposite reaction, which means that if I push on you, you're pushing on me with the exact same force back, just in the opposite direction.
So it's force 2 minus the force of first mass again?
Yeah, the force on mass 1 by mass 2 will be equal to the negative of the force on mass 2 by mass 1. So if 2 masses exert a force on each other, they will, the 2 forces have to be in opposite direction, okay? And the same size.
So in the plate tectonics and stuff, and you've got one plate going this way, you've got one going this way. Is that different then, or is that still?
No, that'll have to be it'll have to be the same thing. So, you know, let's let's say, we have three types of plate boundaries, right? Like, what are the types of plate boundaries? We'll expand people's horizon. Going together, pulling apart, and then transform. Okay, yeah. The only transform one's like San Andreas Fault, pretty much, I think. What's the other one? Oh, there's several of the transforms? Okay. Anyway, yeah, so let's say you have two plates pushing together. I don't know, one plate one and plate two. This one is moving this way and exerting a force on plate two. Well, plate two is actually automatically pushing back on it, the same force. That's what so that'd be an example, okay? Many other examples. Well, if I put this book on the table keeps the book from accelerating downwards, right? And so the table's pressing on the book. Well, clearly the book's also pressing down on the table, with the same magnitude of force. And as an example of this, actually, let's do a little example. Newton's third law example. In order to do this example, I'm going to introduce one concept which we'll be using quite a bit. That is, the concept of free body diagrams. Sometimes they also get called force body diagrams. And I'll give a little acronym, FBD, free body diagram. So let's consider the book on a table. So table, let's try and draw it. It's on the table, it's probably not levitating. So a book resting on a table. Human beings are pretty good at being able to just kind of picture what the forces are on an object. Remember, a force is a vector, so you can think of it as an arrow. The reason we're pretty good is that's what we deal with in daily life all the time. And the reason you can walk is your mind's automatically processing all these things without you even knowing, all these forces without you even having to think about it. The free body diagram helps to simplify a situation so we can actually see what's going on. So what I do if I have like a real world situation, like a book on a table, is if I'm interested in the book, or actually for every mass in here, every mass that I'm interested in, I can draw the mass as a little box. Some people can do points, and you can just draw a little box to represent the book. And then you can draw arrows on that box to represent the forces. So for instance, if I have a book sitting on the table, what are the forces on it?
Gravity.
There's a force of gravity going downwards. I'm going to label that with a little F sub g. By the way, it's pretty standard also in the book to label the force of gravity. They call that the weight, and so they often label it with a W. That's also okay. But it's a vector, so we got to make sure we have the vector sign over it. I'm actually, well, I'll leave that like that. I'm going to kind of label that as FG. And then, what's the other force on it?
Force from the table.
There's only force of gravity to fall down, right?
Yeah.
The force from the table.
So you have a normal force from the table. I'm going to call this an N. N is normal force, it's a pushing force. going upwards. Any other forces if it's sitting there that you can think of? See, you guys are pretty good. You identified all the forces on it. Humans are really good. I mean, you can just, I've never seen it so people can identify the forces on a simple object. It's pretty easy. Humans are good at that. So these are the two forces on the object, the weight and or the gravity force and the normal force. All right, and then if we just represent the object as a little box, whatever the shape it is, kind of simplify our diagram of where the forces are going. This is called a free body diagram. Okay. Okay. Well, let's go over to this thing here. We can draw, there's two masses in here. Two objects in here. There's the book and then there's the table. Let's draw a free body diagram for each of these and see if we can label forces on it and see if we can pick out these types of forces, the Newton's third law forces. Okay? Maybe I'll draw a table as a little block like this, okay? So if I draw when we're dealing with free body diagrams, we draw a little box for each of the forces, or for each of the masses kind of separated out. So we kind of isolate each mass and look at the forces on it. So for the table book, I'm going to call this object 1, object 2. So for the book, what are the forces on it? We already drew those, right? You have the normal force. Is the normal force exerted by the table? So that would be a force on object 1 by object 2, right? So I'm going to call this normal force on object 1 by object 2. I could have just put an F here on object 1 by object 2. Maybe I'll do that so it's consistent with this. We'll have consistency with that rule. And then the force of gravity. Okay, if I drew a little free body diagram for object 2, what would I have? What forces are on the table?
Gravity.
You have gravity going downwards. I'll write this F and G. Maybe I'll label that with a 1 and a 2. Okay.
And then the force of the book.
Yeah, and then there's a force of the book, right? The book's pressing on top of it. So there's the force on 2 by 1. Okay. Newton's third law says that this force and this force have the same magnitude, or the arrow is the same length, and then they point in opposite directions. Okay, that's all that Newton's third law says. These are third law force pairs, we call them. You want to see some other? Is this it, by the way? Because it looks like there's only forces pulling it down. The table wouldn't be just falling through the floor. Well, there's like the floor. It has to be a normal force from the floor as well. So, on the table. Good. Some examples of this. All right, let's do another couple of forces.
FG2 was the force of the book on the table.
No, that was a force of gravity on the table.
Which one was the force of, that was F21?
Yeah, this is a force on 2 by 1. So if the book's object 1, the table's object 2. The normal force pressing down on the table. Yeah, force on 2 by 1. All right. We're going to ignore the table now. We're just going to call any forces from the normal force. I have 3 masses here, okay? Let's see if we can draw all the forces on each of these masses. Okay? And I'll let you work on that for a little bit. And make sure you draw free body diagrams. Do that and then circle all the third law force pairs, okay?
You want us to include the table?
What's that?
The
No, you
table.
can ignore the table.
Okay.
Just these three masks. Except for, it's called the force on the table, the normal force, okay? You got it? You ready?
Yeah.
All right. We'll go through this. In order to understand these ones, I think it's just easier to label these with various numbers. I'm going to call this mass 1, this 2, and this object 3, okay? All right. I'm going to draw a free body diagram first of all for 1. That's the top mass. What are the forces on it?
Gravity.
All right. Just so that we get used to various different notations, I'm going to call this the weight on 1. Okay?
And then force of 1 by 2.
Yes. Force on 1 by 2. Very good.
So that would not be force on 1, by 2, by 3?
By 3 also.
Is this touching?
Okay.
As long
Is
as
this
it's not
touching? Is 3 actually pushing on this?
technically.
Yeah, just look at that mass and just look at the forces that are actually on it. Well, you want to be careful. This book isn't actually directly exerting a force on this one. It's placing one.
So
Yes.
if it's not touching, then it's like doesn't count, because you still have a pressure, like a weight holding,
Well, yes, it won't count for a normal force. Normal force, they have to be touching. Okay, the only force that it doesn't have to be touching is gravity. There actually is a gravitational force between these, but it's tiny, tiny, tiny. So we wouldn't worry about it. But for normal forces and tensions, they have to be touching. All right, let's do 2. What are the forces on 2?
Gravity.
Well, we only have, there's only a gravity's only, if we're looking at just 2,
Mm-hmm.
the only gravity force on this is the weight due to 2.
So, yeah.
Okay?
What about force 2 by 1?
There is a force on 2 by 1.
Mhm.
Which way would it go?
Down.
Because mass 1 is pressing on top of it, right?
Mhm.
So, force on 2 by 1. Okay, any other forces?
Force 2 by 3. By
Oh, yeah.
2.
Mass 3 is pushing it upwards.
Mhm.
So, force on 3 by 2. Well, on 2 by 3, sorry. On 2 by 3. And these two diagrams, is there a third law force pair? Let's circle these. Is there a third law force pair between those two diagrams?
Yeah, 1 and 2 and 3.
Cancel out with force 2 on 1.
This, well, they don't cancel out, but those two forces are the third law force pair. This means they're the same magnitude, just opposite in direction.
Okay.
All right, let's do a free body diagram for 3. What forces are directly on 3, are on 3?
So there's a normal force going up, right?
Yeah, there's a normal force, just pulling it upwards.
Mhm.
Gravity.
Mhm.
There's the weight of 3. That would just be the weight of the book.
Mhm.
Doesn't include anything else.
And then the 3 by 2.
Yes, and then there's a mass 2 is pressing down on the book. And so you would have a force on 3 by 2. Okay, let's use a different color of chalk. What's another third law force pair?
Oh yeah. That.
This and this have to be the same size. They're but opposite direction. That's a third law force pair. So third law force pairs are between different masses. You'll never find them on this, they're on different masses. But if you draw a free body diagram for each mass, you'll be able to see those. Does it make sense how to draw a free body diagram? All right, let's see why they're really useful. Yeah.
Why do we disregard the weight of 1, so to speak, on 2 when we're dealing with 3?
Well, we don't disregard it. It doesn't, this isn't actually a force on mass 1. Gravity doesn't actually pull. This is just how much gravity pulls on mass 1. We're just looking at the forces on mass 1. This is just how much gravity pulls on mass 2. This is just how much gravity pulls on mass 3.
So to figure out your actual gravity, you would actually have to combine the 3 of them.
No, you'd have 1 for each. So this, in magnitude, this turns out to be like m2 times g, okay? In magnitude, we'll worry about that in a little bit. But, let's say I'm looking at mass 2, okay? Or actually this one. The weight of these isn't actually included on there. But those 3 push down on it. Those two above it push down on it, and that gives you this force here.
So like what he's saying, it would, if we were doing like magnitude of the vector, it would be larger than, like force 3-2 would be larger than force 2-1.
Yeah, that's right.
It would be twice the size, almost like right around twice the size because of
Maybe I missed.
it's got the 2 masses
Yeah.
instead of.
So the contribution pressing down on that book from the 2 masses above it are in this force on 3 by 2. That's where the contribution is. Okay. And if we actually, when we start to do math on these things to add up all the forces, what you'll see is that force on 1 by 2 is going to be the weight 1, and it's just sitting there. So this becomes weight 1 here in magnitude. That means this is weight 1 plus weight 2. Go down here and you'll get like weight 1 plus weight 2 plus weight 3 to the normal force. But in actuality, it's just a pressing force on it. That's all. And for instance, if I put more pressure on it, I would increase that force. That doing anything to the weights. Okay. We'll do some more examples and hopefully get our heads around this a little bit more. Main thing is, are we comfortable with free body diagrams?
Yes.
Okay, let's do some simple Newton's second law stuff.
It's so long.
You can stop it and restart it.
Do you want me to read?
Yeah, because we're almost